In Talk 1.3, we covered cognitive biases, the systematic errors our brains make when reasoning under uncertainty. Today, we cover a completely different kind of bias, methodological bias in study design and data collection. These are systematic errors built into the way a study is conducted that distort the association between exposure and outcome. And they're one of the three major threats to causal inference we identified in Talk 4.1. Methodological bias is distinct from random error. Random error scatters results unpredictably in all directions. Bias pulls results consistently in one direction. It systematically over or underestimates the true association. This makes bias more insidious than random error because it can't be averaged away with larger samples. A bigger biased study just gives you a more precise wrong answer. In this talk, we'll cover the major categories of bias: selection bias, information bias, and their subtypes. And for each one, we'll look at a veterinary example, how the bias operates, and what you can do to prevent or detect it. We'll also cover lead time and length time bias, which are particularly important for evaluating screening programs. Let's go. Methodological bias falls into one of two fundamental categories, and keeping this distinction clear will help you diagnose what's gone wrong in any study you read. Selection bias is about who gets into the study. If the process by which animals or individuals are selected into a study or into the exposed versus unexposed groups is systematically related to both the exposure and the outcome, you have selection bias. The study sample doesn't represent the target population in a fair way, and the association you observe is distorted as a result. Information bias is about how exposure or outcome is measured. If the measurement of exposure status, disease status, or both is systematically wrong, not random noise, but consistently wrong in a particular direction, you have information bias. The measurements themselves are distorted, and any association derived from them will be distorted too. The concept of bias direction is critically important for interpreting real studies, especially studies that can't be done perfectly. If you can reason about the likely direction of a bias, you can make intelligent inferences about whether the true association is larger or smaller than what the study found. Bias towards the null means the observed association is smaller than the truth. The bias is making the exposure look less associated with the outcome than it really is. This is conservative in the sense that it underestimates risk, but it means real effect gets missed. Bias away from the null means the observed association is larger than the truth. The bias makes the exposure look more strongly associated with the outcome than it really is. This is the direction that generates false alarms, apparent associations that don't reflect a true causal relationship. Let's look at the major subtypes of selection bias with concrete veterinary examples. Bergson's bias, sometimes called hospital admission bias, is a classic problem in case control studies that recruit cases and controls from a hospital population. Hospitalized animals are not representative of the general population. They're there because they're sick, and the range of conditions that brought them in is narrowed by the referral patterns of the hospital. If both your exposure and your outcome are more common in hospitalized animals for independent reasons, you can observe an apparent association that doesn't exist in the general population. The healthy animal bias, analogous to the healthy worker effect in human epidemiology, operates when study enrollment systematically selects healthier than average animals. In a feedlot BRD vaccine trial, the protocol may enroll animals at arrival processing, but animals that are visibly sick at arrival, already showing signs of BRD, may be treated and excluded from the trial. The enrolled population is systematically healthier than the average arriving animal, which means the study underestimates both baseline disease risk and the absolute benefit of the vaccine. Loss to follow-up bias is particularly dangerous in intervention studies. If animals are withdrawn from a study for reasons related to the outcome, adverse drug effects leading to withdrawal, owners of sick animals dropping out because the animals are deteriorating, the animals who remain in the study are a biased sample of those who started. In a chemotherapy trial, if dogs experiencing adverse effects are more likely to be withdrawn, the remaining dogs are relatively tolerant of the drug and healthier than the true treated population. Survival and adverse event rates will both appear more favorable than they truly are. The common thread. In all three cases, the mechanism of selection into or out of the study is correlated with both the exposure and the outcome. That correlation is what creates the distortion. Information bias occurs when the measurement of exposure or outcome is systematically wrong. Let's look at the major subtypes. Recall bias is a particularly important problem in retrospective case control studies that rely on owner or client recall of past exposures. Cases: animals with the disease and their owners may recall and report past exposures differently than controls. If a dog has just been diagnosed with lymphoma, the owner is likely to think carefully and anxiously about everything the dog has been exposed to. They may recall the lawn chemical application 2 years ago. The owner of a healthy control dog has no such incentive. The same chemical application may not be remembered. This differential recall creates an apparent association between lawn chemicals and lymphoma that may be partly artifactual. Observer or measurement bias occurs when the person measuring the outcome knows the exposure or treatment assignments of the animal being measured, and this knowledge influences their measurement. A clinician who knows which dogs receive the new pain protocol will unconsciously rate their pain scores more favorably. The fix is blinding, separating the outcome assessor from knowledge of treatment assignment. This is why double-blinded trials are the gold standard, and why studies that can't be blinded need to use objective outcome measures where possible. Misclassification bias is perhaps the most technically important form of information bias. It occurs when some animals are assigned the wrong exposure or disease status, classified as exposed when they're unexposed, or as cases when they're truly controls. Misclassification comes in two flavors: differential misclassification, where the error rate differs between cases and controls or between exposed and unexposed groups, can bias the association in either direction, toward or away from the null, depending on the pattern. Non-differential misclassification, where the error rate is the same in all groups, typically biases the association toward the null. This is the important result. If a study uses an imperfect exposure classification that is equally inaccurate in all groups, it will underestimate the true association. Correcting for misclassification would reveal a stronger effect than the crude analysis shows. Lead time bias and length time bias are subtypes of selection bias that are specific to the evaluation of screening programs. They're critically important for anyone designing or evaluating surveillance or early detection programs in veterinary medicine, and they're tested on the ACVPM exam specifically in the context of screening. Lead time bias is perhaps the most important concept in screening evaluation. Imagine a disease that kills an animal 3 years after it starts. Without screening, the animal is diagnosed at 2 years into disease, when clinical signs appear, and lives one more year. With a new screening test, the disease is detected at 6 months before clinical signs, and the animal lives 2.5 more years after diagnosis. It looks like the animal survived 1.5 years longer because of screening, but the animal still died at 3 years into disease, exactly the same time. Screening just moved the start of the clock. The apparent survival benefit is entirely artifactual. It's lead time, not real survival gain. The fix is to measure survival from a fixed reference point, time of exposure, time of birth, or calendar time, not from time of diagnosis. When time of diagnosis is the starting point and screening moves diagnosis earlier, lead time bias is guaranteed. Length time bias operates through a different mechanism. Screening programs operate at intervals, annual, biannual, monthly. Rapidly progressive diseases develop and cause clinical signs between screening intervals and never get caught by the screen. They present as symptomatic cases. Slow-growing, indolent diseases are present for months or years before causing symptoms and are much more likely to be caught during a routine screening test. The result: screened populations appear to have a disproportionate number of slow-growing, less aggressive diseases, and they appear to do better. But this isn't because the screening works. It's because the screen is preferentially selecting animals with naturally favorable disease courses. Now, let's be practical about what you can actually do about bias, both when designing studies and when reading them. For selection bias, prevention requires thinking carefully about how animals are selected into and out of the study before data collection begins. Using population-based sampling rather than convenience samples, selecting controls from the same population that produced the cases, and minimizing and carefully documenting loss to follow-up are the primary tools. During critical appraisal, compare the baseline characteristics of exposed and unexposed groups, or cases and controls. If they look systematically different in ways that are related to the outcome, selection bias is operating. For recall bias, prevention is best achieved by collecting data prospectively before outcomes occur, so recall can't be influenced by knowledge of outcome. If retrospective collection is unavoidable, using medical records rather than owner interview where possible and blinding interviewers to case status reduces the differential recall problem. For observer and measurement bias, blinding is the gold standard. When blinding is impossible, use objective, quantifiable outcomes that require minimal interpretation. Body weight, serum creatinine, tumor size by imaging, rather than subjective assessments that are more vulnerable to observer expectation effects. For misclassification, use validated, high-quality case definitions and exposure classifications. If an imperfect test is used to classify disease status, quantify its sensitivity and specificity, and apply a misclassification correction in the analysis. For lead time and length time bias, the analytical solution to lead time bias is measuring survival from a fixed reference point. Detection during appraisal is straightforward. If survival is measured from time of diagnosis and screening is involved, lead time bias is probable until proven otherwise. The footer on this slide captures the practical reality. No study is entirely free of bias. The goal is not perfection, it's honest identification of likely biases, careful reasoning about their direction, and appropriate qualification of conclusions. The summary. Methodological bias is systematic. It distorts results consistently in one direction, unlike random error. The two major categories are selection bias, who gets into the study, and information bias, how exposure and outcome are measured. Key selection bias subtypes include Bergson's bias, healthy animal bias, and loss to follow-up bias. Key information bias subtypes include recall bias, observer bias, and misclassification bias. Non-differential misclassification pulls toward the null. Differential misclassification can go either way. Lead time bias and length time bias are screening-specific phenomena that make screening programs appear more effective than they are. And throughout all of this, these are methodological biases in study design, completely distinct from the cognitive biases in clinical reasoning we covered in Talk 1.3. The ACVPM exam tests that distinction explicitly. In the next talk, we cover confounding, the third threat to causal inference, and in many ways the trickiest, and its close relative, effect modification. Pause the video and see if you can answer the following questions. We'll then work through them together. This scenario is a carefully constructed teaching case designed to demonstrate how multiple biases operate simultaneously in a realistic study design, a hospital-based case control with retrospective exposure assessment. This design is common in veterinary epidemiology because it's logistically feasible, and understanding its vulnerabilities is essential for critical appraisal. Question 1. Two biases and their mechanisms. Bergson's bias, selection bias. Both cases and controls are recruited from a referral hospital, not from the general dog-owning population. Referral hospital patients are systematically different from the general population. They tend to come from households with higher income, higher health awareness, and potentially different exposure profiles. If dogs with brain tumors and dogs with orthopedic conditions differ systematically in their likelihood of presenting to a referral hospital in ways that correlate with pesticide exposure, the OR will be distorted. Direction, uncertain, depends on the specific exposure referral correlation, but it introduces non-representativeness of the target population. Recall bias, information bias. Owners of dogs with brain tumors cases are likely to have thought intensively about what their dog was exposed to, motivated by grief and a search for causation. They may report pesticide exposures more completely and vividly than owners of dogs with orthopedic controls, who have less emotional motivation to review past exposures carefully. This differential recall will systematically inflate the apparent association between pesticide exposure and brain tumors. Direction, bias away from the null. OR is likely overestimated. Question 2, true OR direction. Given that recall bias is the most operationally significant bias in this design and it inflates the OR, the true OR is likely lower than 2.8. The 2.8 is probably an overestimate of the true association. However, because the 95% confidence interval excludes 1.0, even with this inflated estimate, there may still be a real association, just smaller than 2.8. Question 3. How each change addresses a specific bias. Using veterinary medical records for exposure classification addresses recall bias. Records don't depend on owner memory and are collected without knowledge of future disease status. Both exposed and unexposed animals' records were created before the outcome occurred, making differential misclassification much less likely. Using population-based controls addresses Bergson's bias. Controls are no longer selected from a hospital population with its own selection pressures. Population-based controls are more representative of the dogs from which the brain tumor cases arose, making the comparison more valid. Question 4, does OR equal 1.9 support the bias analysis? Yes, strongly. The OR dropped from 2.8 to 1.9 after addressing recall bias and Bergson's bias. This is exactly what we'd expect if recall bias was inflating the OR in the original study. Correcting it should move the OR toward the null. The association remains statistically significant. 95% CI 1.1 to 3.3 excludes 1.0, suggesting there may be a real association between organophosphate exposure and canine brain tumors, but the magnitude is substantially smaller than the biased estimate suggested. This is a textbook illustration of how identifying likely bias direction allows you to predict and then verify the effect of methodological improvements, and why bias analysis is not just academic, but practically important for interpreting the literature.